Today we're going to talk about exponential and logarithmic equations. Equations, of course, are models of real-life situations, so we need to develop skills that allow us to solve equations that involve logarithms and exponentials. And the very first one comes from, we did allude to this in an earlier lecture. Right, remember that we had a to the x1, if a to the x1 is equal to a to the x2, then x1 must be equal to x2. So we can extend that to, of course, this is base A, so if we specifically talk about base E, then this is certainly true as well. Now, remember that logarithms and exponentials are very closely related to each other, so in this case here, right, if in fact we have two logs of the same base are equal, then of course this comes from the fact that x and y must also be equal. And this is vice versa, it's equivalent to, so it goes both ways. So if x and y is equal, then the log in base A of x equals the log in base A of y. Right, under the normal conditions for logarithms, that x is positive, y is positive, and a is positive, and a is not equal to 1. So in this lecture we're going to talk about skills that will allow us to be able to solve equations, and these are the properties that we're going to use. Right, so let's look at the first example. Right, let's suppose we want to solve 8 to the x equals 21. And we're going to give the solution right to the nearest 1,000. Right, now notice that if we have 8 to the x is equal to 21, normally what we try and do is try and make the same base here, but of course 21 is not going to allow us to make a base 8 or a base 2, which would be the logical ones to look for. So what we have to do is we have to apply this particular rule up here. So we can take the log, right, of both sides. Now it doesn't matter whether we take the natural log or the common log. If we take the natural log, then I'd have this. Okay, and that's in base E, of course. So now we can apply the properties of logs, which says this would be x ln of 8 equals the ln of 20. ln of 8 is a constant, all right, so x is going to be equal to the ln of 21 over the ln of 8. And that will be approximately, if we look at this, all right, with a calculator we'll have the ln of 21 and we divide by the ln of 8. And this gives us 1.4641, and to the nearest thousandth would be 464. So this will be 1.464 to the nearest thousandth. So our solution set is 1.464. Okay, so that's how we do our first one. Right, the second example, all right, is a little bit more involved because we want to solve 5 to the 2x minus 3 equals 8 to the x plus 1. And we're going to give the answer or solution right, give the solution again to the nearest thousandth. Right, so we start with 5 by 2x take 3 equals 8 to the x plus 1. Right, again we've got a base 5 base 8, we can't do anything about that, so we take the log again, or use the natural log, it doesn't matter, you can use the common log, base 10 if you want, but if we have here, we take the natural log of both sides. Now we apply our log properties, which says that the power property says this, or use parentheses to make sure we're clear, that all of this must be multiplied by ln 5, and we have x plus 1 ln of 8. Right, now we need to isolate x, so I'm going to distribute first of all, so I'm going to have 2 ln of 5, all right, times x. If I multiply this by this, right, ln of 5 is a constant, 2's a 5, so I'll put them together, minus 3 ln of 5 equals ln of 8 by x plus the ln of 8. Now I'm going to put all my x's together, so I'm going to have 2 ln of 5 by x minus the ln of 8, bring this to the other side, is equal to the ln of 8, and then I'm going to add 3 ln of 5. I'm going to take out a common factor here, so I'm getting all the numbers together. So the right side stays the same. Now I'm going to multiply by this number here, that's a constant. So we have ln of 8 plus 3 ln of 5 over 2 ln of 5 minus ln of 8. Right, so we're now in a position, all right, to evaluate this using a calculator. All right, so we have the ln of 8 plus 3 times the 5, but the ln of it is equal to this. So this looks like this is going to be, 6.977. I'm going to do this in 2 steps. So this is going to be approximately 6.9077553. Notice that I've gone to many more decimal places than 3. Right, and now I need to, because I'm going to round off at the end. So now, of course, we're going to have 2 times 5, but the ln of it is equal to this, minus the ln of 8, which is this. So I'll end up with here 1.1394, and we did 1, 2, 3, 4, 5, 6, 7 here. So 1, 2, 3, 4, 5, 6, 7, 3, 9, 4, 3, 4, 2. And so this is going to be coming out to, all right, so I can do this fairly easily. I can just find the inverse of this and then multiply it by the 6.9077553. And notice I get 6.062 to 3 decimal places. So it's going to be 6.062 to the nearest thousandth. So our solution set is 6.062. Right, so that's how we do that particular type. So a little bit more involved because we have x's on both sides. Right, let's look at example 3. Right, so we'll break this into 2 examples. Let's do part A. Okay, part A, let's suppose I want to solve, right, each equation. Right, and give the solution again. To the nearest thousand. All right, so part A, here's part A. So we're going to have e to the x equals 200. Right, now e, so we've got an e, so clearly to undo an e, we would take an ln of e to the x and I'd take ln of both sides. Now this tells me that x ln of e is equal to the ln of 200. However, ln of e, these undo each other, so this is like a power of 1, so this would be x by 1 here would be the ln of 200, which of course x is equal to the ln of 200, which when we apply a calculator to this, I end up with 5.298 to 3 decimal places. So our solution set is 5.298. Okay. Right, let's do part B. Right, part B is, let's look at e to the 2x plus 1 by e to the negative 2x is equal to 3e. All right, now this is an interesting question. Right, now notice here that we've got e's, all right, on both sides. So this is like an e to the 1. So what if I was to use my exponential rules first and say, all right, so let's suppose that this would be e to the 2x plus 1 minus 4x, because remember our exponent rule says that when we're doing the product of two numbers of the same base, then you add the exponents. Right, so this is equal to 3e to the 1. So what we have here then is e to the 1 minus 2x equals 3e to the 1. Now the next thing that we'd like to do, of course, is we could divide both sides by e to the 1. So really what this is saying is that I have e to the 1 minus 2x minus 1, because we subtract the exponents here, is equal to 3. So what I really have is e to the negative 2x equals 3. All right, now of course we would apply the ln of both sides. Clearly this becomes 2x, because the ln undoes the e, is equal to the ln of 3, which implies then that x is equal to the ln of 3 over negative 2. Right, so we get our calculator. All right, here it is. And we go 3 ln of it, and we divide by 2, but make it negative 2, and that's equal to, right, negative 5.549 to 3 decimal places. And so our solution set is negative 0.549. Okay, so that's how we do that type. All right, let's look at example 4. All right, let's suppose now we want to solve, right, e to the 2x minus 6e to the x plus 5 equals 0. And again, in this case, we want to give the exact value or values for x. Right, so what we have here is e to the 2x minus e to the x plus 5 equals 0. Now, if you look at this carefully, what I really have is e to the x squared minus 6e to the x plus 5 equals 0. And if I let, say, just u, for example, equal to e to the x, then what I really have is u squared minus 6u plus 5 equals 0. With this as a quadratic form, which we did earlier in the course, just that it's in e's. All right, so we need to look at factoring this, and we can see that factors of 1 and 5 work, but negative 1 and negative 5. Make sure you FOIL it out to make sure it works. U squared minus 5u minus u is minus 6u plus 5, so that's true. So now I have u minus 1 equals 0, or u minus 5 equals 0. So u is equal to 1, or u is equal to 5. But remember that u is e to the x, so e to the x equals 1, or e to the x equals 5. So I've got two equations to solve here. All right, so how do I undo an e? Well, I'll take the ln. So if x is equal to the ln of 1, but of course the ln of 1 is what? 0. That's the exact value. Here, of course, the ln of e to the x will be the ln of 5. So x will be the ln of 5, so I need a calculator to, well, I guess we leave it in exact, we want the exact answer, so we need to leave it like that. So our solution then is going to be 0 and ln of 5 are the exact solutions. All right, now the next one. Right, you can see here's a lot of techniques, and we're going to now talk about logarithmic or equations. So I'll do a couple of simple ones. All right, so let's suppose we want to solve each equation. All right, and give exact values. All right, so part A is, let's suppose we have 4 ln of x equals 36. So let's look at this one. So notice here that we have 4 ln of x. So we need to first of all isolate ln of x, and we'll do that 36 divided by 4, which is 9. So what I really have is ln of x equals 9. Now to undo an ln, we raise it to e to the power of ln. So the exponent or exponential e, all right, undoes the ln's, leaving me with x, and this is going to be e to the 9. Okay, so that would be the exact answer. So our solution set is e to the 9. All right, let's do part B. Let's suppose I want to solve log in base 3 of x cubed minus 5 is equal to 1. All right, so what do we have here? All right, so we need to undo these somehow. All right, now the way we can undo a log in base 3 is, of course, use the exponential of base 3. So let's raise both 3 to both sides of what's here. So in other words, we're using this one here. All right, using the logs. All right, so the inverse process, if you like. All right, the inverse process of log in base 3 is exponential in base 3. So this undoes this, so I've got x cubed minus 5 now is going to be equal to 3, because 3 to the 1 is 3. So now I add 5 to both sides, I get 8, and now find the cube root of x cubed. Take the cube root of both sides, so I end up with x is equal to 2. All right, that's the only answer, so the solution set is 2. Okay. All right, so that's a couple of simple log ones.